Hey everyone, so you've probably seen this before, right? You take a couple of different metals, stick them in a lemon, and somehow you get electricity. How does that work? Well, I promise you, it's not magic, it's just really, really cool chemistry. So today, let's break down the science of how a simple battery really works.
Yeah, this is the classic science fair project, and it gets right to our big question. How in the world can a piece of fruit become a battery? I mean, powerful enough to light up a little LED? Well, to figure that out, we got to start with the basics. What even is a battery? Or, more accurately, a chemical cell?
At its heart, a chemical cell is just a neat little device that takes the energy stored in chemicals and converts it into usable electrical energy. It's all about kicking off a chemical reaction that gets electrons moving, and that flow of electrons, well, that's what we call electricity.
And believe it or not, the recipe to make one is super simple. You only need two key things. First up, you need two different types of metal. Scientists call these electrodes. And second, you need a liquid that can conduct electricity. That's called an electrolyte.
So the electrodes, you can think of them as the on-ramps and off-ramps for the electricity. They're the terminals of our battery. In our lemon example, these are just the two metal strips we jam in there, like maybe a piece of copper and a piece of magnesium.
Now, the electrolyte, this is the secret sauce that completes the circuit on the inside of the battery. It's a liquid that's just swimming with charged particles called ions. Basically, they're just atoms that have an electrical charge. And for our lemon, that acidic juice is the perfect electrolyte.
Okay, now this is the absolute key to the whole thing. You might be wondering, why can't I just use two copper strips or two zinc strips? Why do the metals have to be different? Well, the answer is that there's a kind of chemical competition going on between them.
Honestly, it's like an electron tug of war. See, different metals have different, let's call it a desire, to give away their electrons. A metal like magnesium is super generous. It really wants to get rid of its electrons. Copper, on the other hand, is kind of stingy. So when you connect them both in our lemon, the magnesium gladly gives up its electrons, and that makes it the negative pole of our battery. So here's how it all plays out. Step 1. The magnesium, our more reactive metal, lets go of its electrons. Step 2. Those electrons can't really swim through the lemon juice, so they take the easy way out. They zip down the wire that you've connected. Step 3. They travel all the way to the less reactive metal, the copper. And finally, to keep the whole thing going, ions move through the electrolyte, the lemon juice, to complete the circuit.
You know, a great way to think about this comes from our source material. A chemical cell is basically an electron pump. That difference in reactivity between the two metals creates a kind of electrical pressure. We call it voltage that literally pushes electrons out of one metal and pulls them into the other.
So that begs a question, right? How do you know which metal is going to be the giver and which one's the taker? And how can you guess how powerful that pump is going to be? Well, it all comes down to a kind of secret rule book for chemists. It's called the electrochemical series, but I just like to call it the reactivity ladder. And the rule for using this ladder is so simple, you're going to love it. The farther apart two metals are on this ladder, the bigger the difference in their desire for electrons, and the higher the voltage of your battery. So look, pairing magnesium with copper gives you a big voltage because they're far apart. But pairing lead with copper, much smaller voltage. The main takeaway is, the bigger the gap, the more powerful the pump. Simple as that. But there's a catch. Our simple little lemon battery, where everything's just kind of sloshing around together, it has a fatal flaw. It makes it super inefficient, and it means it won't last very long at all. The problem is something I call a chemical shortcut. Now to see this better, let's imagine we swapped our lemon juice for a more potent electrolyte, like a copper salt solution. What happens is the magnesium strip starts giving its electrons away directly to the copper ions that are floating right next to it in the liquid. This is called a displacement reaction. And why is this a huge problem? Because those electrons are now completely useless to us. They took the easy route. They never went through the wire, which means they never powered our little light bulb. It's basically an internal short circuit that just drains the battery's power for no reason.
So how do we stop this chemical shortcut? Well, the solution is actually brilliant, and it's pretty simple. We just separate the two sides. If we stop the metals and their solutions from directly touching, we can prevent that unwanted reaction. We create two half cells.
Okay, but hold on, now we've got a new problem. By separating everything, we've broken the internal circuit. The ions can't flow anymore, so the whole thing just stops working. So, how do we connect the two sides to let the ions flow without letting the main solutions mix and cause that short circuit again?
And this is where the hero of our story comes in. It's a simple but amazing little device called the salt bridge. This is the key to making a much better, much more efficient battery.
A salt bridge sounds pretty fancy, but it can be as simple as a piece of filter paper soaked in some salt water, like potassium nitrate. Its whole job is to act as a bridge that only allows ions to cross. It's like a special ion-only highway connecting our two half cells.
So this little paper bridge has two super important jobs. First, it completes the electrical circuit, allowing those ions to flow so the whole thing can work. And second, it keeps the electrical charge in each half cell balanced. Without it, you'd get a charge buildup that would just stop the reaction cold.
So, when you put all these improvements together, the two separate half cells, each with its own metal and solution, connected by that all-important salt bridge, you get the blueprint for a proper, efficient battery. This classic design is called the Daniell cell.
Let's peek inside. On one side, we have our negative pole, the anode. That's a zinc strip sitting in a zinc sulfate solution. Here, the zinc atoms are literally dissolving into the liquid, leaving their electrons behind on the metal. On the other side, we have the positive pole, the cathode. That's a copper strip in a copper sulfate solution. And here, the exact opposite happens. Copper ions from the solution grab those incoming electrons and plate themselves onto the strip as solid copper metal. And get this, the overall chemical reaction here is exactly the same one that caused our short circuit before. But now, because we've cleverly separated the components, we force those electrons to take the long way around, through our external wire, powering whatever we've connected along the way.
So what kind of power are we talking about here? How strong is this electron pump? Well, this classic zinc-copper setup gives you a nice, steady 1.1 volts. It's not going to jump-start your car, but it's reliable, it's efficient, and it's just a perfect example of how these principles come together.
So there you have it. The secret to a battery isn't magic at all. It's just a clever game of electron tug-of-war. And now you know the rules, all governed by that reactivity ladder. So I'll leave you with a final thought. If you had that ladder in front of you, what two metals would you pick to build the ultimate, most powerful battery you could? Something to think about. Thanks for joining me.